Cool. Welcome back. Hopefully the weekend was refreshing. What are we working on today? There's only one more group of senior design presentations, so I'm ready to jump back into some other courses. Unpause. I think Friday we spent some time just talking about like different integration methods for that pendulum. I think that's where we left off on Friday. Yeah, we saw that Euler is notorious at over predicting like how much the slope is going to affect the solution. Meanwhile, like implicit methods that have some kind of convergence criteria, they've got a nice like they won't move on until you at least have a solution that makes sense. Sometimes it's worth it, other times, I don't know. Nothing else going on. Loading, yeah. Check in as we're loading up.
It's really weird, and there's no jerk in it. Also, my so it makes code more real. Especially when they it's not like
Keyboard.
An external keyboard.
Yeah.
Connect my phone and just
Yeah,
exactly like that.
So what he said was that whatever the class average is for the project, for that divided by 49, so the term average is going to be multiplied by your x. So you get x 75 average of yeah. So the class average for the class average for the team is 49. Yeah. Whatever the class average for the final is, it's greater than the midterm. That number divided by the midterm. We can leave that is going to be multiplied by that's where your metrics go. So when you it's crazy because if we actually do it makes sense. Very how much is the regrade?
Well, your differential equation doesn't need initial. It's just describing your differential equation. Sorry. So your function is differential equation. Those are the same math.
Yeah.
So where you give it a state and then gives you the derivatives of each of those values. Give it a state. Give it so for spring, just a spring natural gas, the operation is negative W squared x. The last one we will pay for no, that's part of your station. Your first that's part of the station. Yeah, so your state position Oh, well, then you have to run spring mass of something. So it didn't run the function, it's created a variable called spring mass. You do kind of the ending. Okay. Well, at least in the line, let's say, for I, the function, so like that line of code is you can. But I think that question was asking use that. So scroll back up to how you set that. It's always the same exact process. You set up a time, set up a state, 0, something. After. Yeah, you can get that thing creating place. Yeah, so anyone change in the field, they not take care of it. Change it in they dot. Yep. Yeah. Oh yeah. Yeah, you're just changing engine to spring. So we were just talking about like this hewn step and spring mass, trying to find one, like how do we integrate this problem, and then also the next step is how do I know that my integrations work and how fast is that happening? Like if time step decreases by 1/2, if it's half of what it used to be, how much is that saving me? Like how much better is my answer? And that's what this process of convergence, when you're finding like the order of convergence on a log plot. If things are 10 times smaller, are you getting 10 times better answer, 100 times, 1,000 times? Like, so that's what we're trying to figure out here. So hewn step, we can grab this from the reading. I know I've seen people ask ChatGPT for an implicit hewn step, and it gives some weird answers. So like if you want a hewn step that's definitely a hewn step, grab it from the reading. If you want to roll the dice and ask an AI for a hewn step, I mean, I don't know, enjoy, but it's not always what you think it should be. So and again, I think we were talking about this on Friday. Like the main thing that makes something implicit is that it's got some kind of convergence check. And it's always the same kind of process of like, all right, go to the next step, do some calculations, and update that next step. Did it change? Yes, no, it changed. Okay, do it again. Did it change? Like, nah, not much. Okay, move on. Next step. Move on to the next time step. All right, so we're going to use that hewn step. We want to define, let me just, because we can go from scratch, right? I know how to define a spring mass system. Def, and we'll go bare bones, right? State. My spring mass is going to have a state. The state is, that this will be my one doc string, X and V. So I'm going to write it out like that, where I can actually use the values of X and V. You don't have to. You can use like state 0, state 1, but sometimes it's nice to like inform your future self of like, hey, by the way, remember when we defined the state for a spring and a mass, the first input was X, the next input was V, velocity, position, velocity. Maybe I could even write that, right? Be nice and friendly to future Ryan. He's getting older, he forgets stuff. The change in that first state is dx dt, so that's got to be V. And there's no other definition, like there's no other like differential equations there. It's just a definition that if I change X, I have that dv, that V has to match however much X changes every step. and then A is going to be negative like W squared times X, so some kind of like natural frequency squared. We were being fancy before, and we said like, okay, let's plug in a W equals 2 up there. And so we'll have a default variable of W that is 2. Or 4 would be nice, so natural frequency is 2, whatever. Then I want to return the array that I get back should be the same shape as the array that I put in. So if I give it 2 values, I need derivative of 2 values. So my first one is that dx dt, and my next one is A. Cool. I don't like to do anything until I can actually see that it works. So let's try something. We'll say I'm 1 meter away, moving 5 meters per second. The derivative of my 1 meter is 5 meters per second, because that's how fast I said I was moving. And the derivative of my velocity, because I'm 1 meter away, is -4. And I'll double check that that makes sense. I have 2 squared negative times 1, so -4 meters per second back to the left. So it seems like I'm getting the right values. And they're in the right shape. That's the main thing. If I give it 2 values, I get 2 derivatives. I can define time. I am the almighty creator of time in this simulation, so I can define it however I want. I'll try 4 seconds. Let's take 51 steps. dt is going to be whatever change in time that happens to be. State. We were just playing around with zeros and empty like. It turns out empty like is like slightly faster. So if you want to try that, it works. Empty like. For every point in time, I want to define the state. I don't know what they are. I'm just filling it up with empty values. But I do know that I have 2 states at every point in time. My first state is my initial conditions, 2 meters and 0 meters per second. So I'll have like some kind of cosine wave that I'm trying to converge to. And now for every other state, for I in range 1, because I don't need state 0, I'm gonna solve for all of those. And let's plot. I'm just going to plot the state to look at position and velocity all in one go. Oh, what did I do wrong? Setting an array element with a sequence. Didn't like that. Still doesn't like that. What if I use zeros? Does it care then? Weird. Then it works. What? I don't know why it didn't like the empty array, but it didn't like it. Does it like empty? Empty is fine. Anyway, So now I have like everything all in one plot. Start at 2 meters, swing down to -2, come back to 2, start coming back. Start at 0 meters per second, but I'm moving towards 0, so I have negative, goes down to -4. But it looks like a cosine wave and a sine wave, which is what I would expect for simple spring attached to a mass. No friction, no damping, none of the fun stuff. No like multi-degree of freedom. But the original question was like, how is this thing converging? So if I increase dt, my delta t, it still looks like a cosine wave. Like, is it worse? Is it good enough? And the bigger the time step, the less time my computer needs to like spend calculating stuff. So if I'm going to end up running this a lot, then like if I'm using it in a microcontroller or something, I would want time steps to be as big as possible, so I'm not dealing with like extra computing stuff on top of other things that I'm trying to do. So we need to look at convergence, like what's the best bang for my buck? Do I want to start here? So if I know that this thing should be a cosine wave, at least like for my position, I can define error really however I want. It's all going to converge at the same rate. Like I could take a cosine wave and subtract it from every one of these points of my cosine wave, and then take the average, or take the sum, or I don't know, something. I could like use any kind of complicated measure, but at the end of the day, it's all going to decrease at the same amount. So one way to do this is just take the last value of the state, subtract it from a known function that I think it's going to be. Oh. So I'm going to take that dt and plot state -1 and 0 minus exact of t -1. So the result of all that work that I did to get that sine and the cosine wave is all one data point so far. So I've only done, I can't draw a line through one data point. I need to do multiple time step sizes. So let's do multiple time step sizes. I'll take everything that I just did, turn it into a for loop. For n in, so we did 21. Let's try like 51, 101, 501, 1001, 5001. I keep adding 1 so that I get like nice delta t values. You can do 20, 50, 101. And then I just want to replace this 21 with an n. And yeah, let's leave it like that. So right now I'm taking dt versus just the absolute error of the exact versus that last value of the state. And let's just see what happens. something's happening. But it's kind of hard to see what's happening because the changes, like the gains that I'm seeing are all happening on like an order. Like if delta t decreases by 1/2, really I'm getting like error decreasing by by 4x, like 4 times better. So it's hard to see that on a linear plot. So let's throw it all onto log and log. So log of the delta time step, log of the actual error, and oh, we should probably take some absolute values, right? Because I don't care if it's plus or minus. Looks like that doesn't look right, right? At least I don't think it looks right. Maybe maybe other people say like, who knows? What am I doing wrong there? Why is it so big in that point? Let's do a quick. Oh, too many brackets there. So we should be seeing order 2 convergence, but we're not seeing that. Not at all. Oh, that's not dt. That's n. I'm just trying to save all my dt vals. Oh, whoops, that's what I was gonna do. I was just trying to append that dt. I don't know, man. Doesn't look second order convergence. I'm doing something wrong, right? Spring mass, W. That should be the answer. 2 times cosine t. The last row of column 0 should be position. And then this should be the last step in time. Am I just not looking at enough? It's that blue one, that first. I don't know. Doesn't look right. So the things that I was playing around with was like the range of like how long I'm solving for versus what those time steps are. 1001, 5001. That's weird. Why is the error? I'm doing something wrong, right? Do I not know how to do I not know how to solve this problem? Oh my god. Did I do the wrong? No. Beta of omega squared. Oh. Yeah. So it should be W times 2, right? This should be 2. I just don't remember. Helps so I should be like writing this out, but I'm doing it all on the fly instead. So my exact, if my frequency is W equals 2, my solution is cosine of 2 times t, not square root of 2t. Now we're starting to see like actual convergence rather than trying to converge to a solution that's not correct. But now this one looks like a second order convergence because I'm plotting dt vals squared and that value of error. And if I want to change how much it's offset, I can like bring it up by a factor of 10, make it like a dashed line, like a black dashed line. And I can see that sure enough, most of my convergence spots are along that dashed black line, which is a slope of 2. All right, making progress. So it does work as long as you can do math and no one's watching. Note to self, W equals 2. So yeah, I was taking square root too many times because the square root of 2 squared is 2, not square root of 2. It's like the quartic root. I don't know why we'd need that. flies. Time flies on a log scale. We were down here at 10 to the 0 hours. Now it's 10 to the 1 hours. All right. Thanks for joining. See you again on Wednesday.